What's the smallest thing? It seems like a simple question. You could say a grain of sand, but you can break that down. You could say a dust mote, but you can break that down too. We keep asking this question, going smaller and smaller, and the journey to find the answer gets very strange very quickly. It forces us to rethink what a thing even is. Let's start with something we can all imagine. Take a single grain of salt from a salt shaker. It's tiny, you can barely see it. But in the world of the very small, that grain of salt is a mountain range. It's a metropolis. And it's made of a staggering number of molecules. Each molecule is a specific arrangement of sodium and chlorine atoms, all locked together in a crystal structure. Billions upon billions of them in that one tiny grain. So a molecule is smaller. Let's zoom in on one of those molecules. But even that isn't the bottom. A molecule is made of atoms. In our case, one sodium atom and one chlorine atom. For a long time, we thought atoms were the end of the line. The word atom comes from the Greek word atomos, which means uncuttable. It was supposed to be the fundamental, indivisible building block of everything. And for a while, that was a good enough answer. Atoms are incredibly small. If you blew up an apple to the size of the Earth, the atoms inside would be about the size of the original apple. They are the basic units of chemistry. Everything on the periodic table hydrogen, oxygen, iron, gold is a different kind of atom. But it turns out they are not uncuttable at all. We figured out that an atom has parts. It has a center, called the nucleus, and it has other things whizzing around that nucleus called electrons. The picture we learn in school is often like a tiny solar system. The nucleus is the sun, and the electrons are planets orbiting it. This isn't quite right, but it's a useful starting point. It's more accurate to think of the electrons as a fuzzy cloud of probability, a region where the electron is likely to be. They don't follow a neat, clean path. The first thing you notice when you look at an atom is that it's mostly empty space. Almost all of its mass is packed into that tiny, dense nucleus. The electron cloud that defines the atom's size is huge and whisper-thin in comparison. If the nucleus were a marble in the center of a football stadium, the electrons would be like gnats flying around the cheap seats. The space between them is just space, so the solid table in front of you is a bit of an illusion. It's mostly emptiness, held together by powerful forces. So now we have smaller things, the electron and the nucleus. The electron, as far as we can tell, is a truly fundamental particle. We have never been able to break one open and see smaller parts inside. It seems to be a basic ingredient of the universe. So is the electron the smallest thing? Maybe. It's a candidate, but what about that nucleus? The nucleus is not fundamental. It's a tightly packed bundle of even smaller particles. We call them protons and neutrons. Protons have a positive electric charge. Neutrons have no charge at all. The electrons whizzing around on the outside have a negative charge. The attraction between the positive protons and the negative electrons is what holds the atom together. So, are protons and neutrons the smallest things? For a while, we thought they might be. They are incredibly small and dense. They make up almost all the mass of you, me, and everything we can see. But then we built bigger and more powerful machines. We started smashing these particles together with incredible force. And when we did, we saw that they weren't solid little balls either. They shattered. And they shattered into even smaller, more bizarre particles. These are the quarks. This is where reality starts to feel less like a set of building blocks and more like a set of abstract rules. A proton is made of 3 quarks, specifically 2 up quarks and 1 down quark. A neutron is also made of 3 quarks, 1 up quark and 2 down quarks. These names, up and down, don't mean anything about direction. They're just labels, like flavors of ice cream. Physicists came up with a bunch of whimsical names for quarks. There's also charm, strange, top, and bottom. So a quark is smaller than a proton. We've gone another level down. But quarks are weird. They have a property that no other particle we've ever seen has. You can never, ever find a quark by itself. They are always stuck together in groups of 2 or 3. The force that holds them together, called the strong nuclear force, is incredible. It actually gets stronger the farther you try to pull them apart. It's as if they were connected by a rubber band that gets infinitely stiff when you stretch it. If you pump enough energy into a proton to try and pull a quark out, the energy you put in will just create a new pair of quarks from the vacuum, which will immediately bind with the ones you were trying to separate. You don't get a free quark, you just get more particles made of quarks. Because we can't isolate a quark, it's hard to talk about its size. But our best theories and experiments tell us that quarks, like electrons, are fundamental. They seem to be true, indivisible points. They have no internal structure that we can find. They have no size. This is a really difficult idea to wrap your head around. How can something exist and have properties like mass and charge, but have a size of 0? Building a point with 0 dimensions, it seems like it shouldn't be possible. It's a mathematical ideal, a perfect point. And this is the picture painted by our most successful theory of particle physics, the Standard Model. The Standard Model is like a complete inventory of the universe's fundamental ingredients. It lists all the particles we know of that can't be broken down further. There are two main categories. There are the matter particles, which are quarks, and another family called leptons. The electron is a lepton. There are also heavier, unstable versions of the electron called the muon and the tau, and for each of these, there's a ghostly, nearly massless particle called a neutrino. So you have 6 quarks and 6 leptons. These 12 particles make up all the matter we've ever seen. Everything in the universe, from stars to puppies to your own brain, is made of combinations of up quarks, down quarks, and electrons. The other 9 particles are more exotic and only show up in high energy situations. Then, the Standard Model lists the force-carrying particles. These are the particles that communicate the fundamental forces of nature. The photon is the particle of light, and it carries the electromagnetic force. Gluons are the particles that carry the strong force, gluing quarks together inside protons and neutrons. Then there are the W and Z bosons, which carry the weak force, responsible for certain types of radioactive decay. And finally, there's the Higgs boson. It's a particle associated with a field that permeates all of space. The interaction of other fundamental particles with this Higgs field is what gives them their mass. According to the Standard Model, all of these particles of the 12 matter particles and the force carriers are point particles. They have 0 size. So the question, how does the smallest thing, gets a very strange answer from our best tested theory of physics. The answer is a whole bunch of things are tied for the smallest. An electron, an up quark, a photon, a gluon. All of them are fundamental points. But this answer is deeply unsatisfying to physicists. It feels wrong. The idea of a point with 0 size but finite mass or energy leads to mathematical absurdities. If you cram all of a particle's mass and energy into a space of 0 volume, its density becomes infinite. This is a singularity. And in physics, when you get an answer of infinity, it's usually a sign that your theory is broken. It's a signal that there's something you don't understand, that you're trying to use your equations in a situation where they no longer apply. This is the frontier of physics. This is where we leave behind what we know and enter the realm of what we think might be. We have 2 great theories that describe the universe. We have general relativity, which describes gravity and the universe on a very large scale, planets, galaxies, the expansion of space. And we have the Standard Model of particle physics, which uses quantum mechanics to describe the world of the very, very small. Both theories work perfectly in their own domains, but they don't work together. They speak different languages. When you try to describe a situation where you have a huge amount of mass and energy in a tiny space, like the center of a black hole or the very first moment of the Big Bang, the 2 theories give you nonsense. This suggests that our idea of point particles is probably just an approximation. It suggests there must be something smaller, some deeper structure to reality that we haven't found yet. So, what could be smaller than a point? This leads us to one of the most famous and controversial ideas in modern physics, string theory. String theory proposes a radical new answer. It says that if you could zoom in on an electron or a quark to an unimaginable degree, you wouldn't see a point. You would see a tiny, vibrating, one-dimensional loop of energy, a string. All the different fundamental particles we see are not different things at all. They are all the same fundamental object, a string just vibrating in different ways. Think of a violin string. Plucking it in one way gives you one note, like a C. Plucking it another way gives you another note, a G. It's the same string, only the vibration is different. In string theory, a string vibrating in one particular pattern would appear to us as an electron. A string vibrating in another pattern would appear as a photon. Another vibration would be a quark. It's a beautifully simple and elegant idea. Instead of a whole zoo of different point particles, you have just one basic entity, the string. Matter particles and force particles are unified into one framework. More importantly, string theory solves the problem of infinities. Because the fundamental object is a string and not a point, it has a tiny but non-zero size. It's not a zero-dimensional point, it's a one-dimensional object. This slight extension in space is enough to smooth out the the mathematical problems. It gets rid of the singularities that plague our current theories. It naturally combines quantum mechanics and gravity, which is the holy grail of theoretical physics. So, is a string the smallest possible thing? According to string theory, yes. These strings would be mind-bogglingly small. If an atom were magnified to the size of our solar system, a string would be the size of a tree. They are far, far too small to be seen with any machine we could possibly build. But string theory comes with its own baggage. For its mathematics to work, it requires the universe to have more than the three spatial dimensions we experience: length, width, and height. It needs something like 10 or 11 dimensions in total. So where are these extra dimensions? The idea is that they are curled up on themselves, compacted down to a size so small we could never notice them. Imagine a long, thin garden hose stretched across a field. From far away, it looks like a one-dimensional line. You can only move forward or backward along it, but if you were an ant standing on the hose, you would see that it has a second dimension. You could walk forward and backward, but you could also walk around the circumference of the hose. That second dimension is small and curled up, so you only see it when you're very close. String theory suggests that space itself is like that. At every single point in our familiar 3D space, there's a tiny, curled up shape of extra dimensions. This is all deeply theoretical. There is currently no experimental evidence for string theory. It's a mathematical framework that is very promising, but it's not yet science in the way that the Standard Model is. It's a candidate for a deeper theory, not a proven fact. So while a string is a very compelling candidate for the smallest thing, we can't say for sure that it's the right answer. This brings us to another, perhaps more fundamental limit. It might be that the smallest thing isn't a particle or a string at all. It might be the smallest possible unit of length itself. This idea is called the Planck length. The Planck length isn't a physical object. It's a fundamental scale built from the basic constants of the universe: the speed of light, the strength of gravity, and the constant from quantum mechanics known as Planck's constant. When you combine these numbers in a certain way, you get a length. And that length is about 1.6 times 10 raised to the power of 35 meters. It's a number so small, it's almost meaningless. A million, billion, billion, billionth of a meter. It's to a single atom what a single atom is to the entire observable universe. It is the shortest possible distance that has any physical meaning. Why? What's so special about this length? It's the scale at which our current understanding of reality completely and utterly breaks down. It's the scale where gravity and quantum mechanics become equally important, and we don't know how to handle that. Imagine you want to measure something very small. To see a small object, you need to probe it with something with a very short wavelength, like a high-energy particle. The smaller the thing you want to see, the more energy you have to pack into your probe. Now, imagine you want to measure something as small as the Planck length. To do that, you would need to concentrate an enormous amount of energy into a tiny point in space. But what happens when you cram a huge amount of energy into a tiny space? According to Einstein's general relativity, energy and mass are equivalent EMC2. And mass warps space-time. If you concentrate enough mass or energy in one spot, you create a black hole. And here's the catch. The amount of energy you would need to probe the Planck length is so high that your probe itself would collapse into a tiny black hole. This black hole would have a size, an event horizon, that is roughly the Planck length. So the very act of trying to look at something that's small would create a black hole that would swallow and hide what you were trying to see. You can't measure a distance shorter than the Planck length because the measurement itself would prevent you from seeing the result. This suggests that the Planck length might be the fundamental pixel of the universe. That space itself isn't smooth and continuous, but granular. Like a digital image on a screen, if you zoom in far enough, you see the individual pixels. You can't have a detail that is smaller than one pixel. The Planck length could be the size of those cosmic pixels. Anything would have to be at least this big. Any movement would be a jump from one pixel to the next, not a smooth slide. If this is true, then space, at this fundamental level, is a chaotic, bubbling mess. It's sometimes called quantum foam or space-time foam. Tiny fluctuations in energy would be constantly creating and destroying tiny virtual particles and microscopic black holes, all winking in and out of existence in a fraction of a second. In this view, the calm, stable space-time we experience is just the large-scale average of this underlying quantum chaos. So we have a few possible answers now. The smallest things could be the fundamental particles of the standard model, like quarks and electrons, which we believe are mathematical points. Or they could be tiny vibrating strings, the building blocks of everything in string theory. Or maybe the question is flawed. Maybe the smallest thing isn't an object at all, but the Planck length, the fundamental, indivisible unit of space itself. Below that length, the very concepts of space and distance may cease to exist. And this forces us to confront the biggest problem of all. Our very idea of a thing is probably wrong. We think of things as little solid objects. A grain of sand is a little rock. An atom is a tiny ball. An electron is an even tinier ball. But that's not how the universe works at the quantum level. A particle, like an electron, is not a solid object. It's a wave of probability. It's a localized excitation in a field. Think of it like this. There is an electron field that fills the entire universe, everywhere. When you add a bit of energy to that field at a certain spot, it creates a ripple, a concentrated bundle of the field's properties. That ripple is what we call an electron. When the electron moves, it's the ripple that's moving through the field. The particle isn't a thing moving through space, it's a phenomenon of the field itself. This is true for all the fundamental particles. There is a quark field, a photon field, a Higgs field. The universe is not a collection of tiny billiard balls bouncing around in an empty void. The universe is a collection of overlapping, interacting fields, and what we call particles are just the vibrations, the quanta, of these fields. So what does it even mean for a ripple in a field to have a size? The question starts to lose its meaning. It's a question based on our everyday macroscopic intuition, but that intuition doesn't apply in the quantum realm. Furthermore, the act of observing a quantum system changes it. This is the famous Heisenberg uncertainty principle. You can't simultaneously know a particle's exact position and its exact momentum. The more precisely you measure its position, the less you know about where it's going. The more you know about where it's going, the less you know about where it is. Reality at this level is fundamentally fuzzy, a world of probabilities, not certainties. So, when we ask what is the smallest thing, we are imposing our human-scale ideas onto a part of the universe that doesn't play by our rules. We are looking for a simple, solid answer in a place that is made of probability waves and vibrating fields. So, where does that leave us? The honest answer is, we don't know for sure, but we have a layered understanding. For all practical purposes, the smallest things we have ever directly dealt with and manipulated are the fundamental particles of the standard model quarks and electrons. Our best measurements show them to be point-like, with no size. This is the most experimentally grounded answer. But that answer comes with theoretical problems, those pesky infinities. This suggests that the point-like nature of these particles is an incomplete picture. To solve those problems, theories like string theory propose a deeper layer of reality. They suggest that the smallest things are actually tiny strings of energy, and their vibrations create everything we see. This is a mathematically beautiful idea, but it remains unproven, and beneath even that, there may be a more fundamental limit. The Planck length, not a thing, but a boundary. The smallest possible distance, the pixel of reality beyond which our concepts of space and time and measurement dissolve into a quantum foam. This is a limit imposed by the very laws of the universe as we understand them. So, what is the smallest possible thing in the universe? It's not a simple answer. It could be a quark, it could be a string, it could be the Planck length itself. Or it could be something else entirely, something we haven't even imagined yet. The search for the smallest thing is really a search for the true nature of reality. It's a journey that has taken us from a grain of salt down through atoms, protons, and quarks to the edge of what we know. We are peering into a world of quantum fields, extra dimensions, and the very fabric of space-time. And the most profound thing we've learned so far is that the deeper we look, the less the universe looks like a collection of things at all.